So we spent the initial session yesterday trying to set up the stage for this discussion of fairness and accountability in machine learning. And I started off with a bunch of different case studies where we see the possible role of automated decision making and how you might think about trying to build such a system and where some of the issues might come up. And some of these issues were raised. We had a good discussion about this. And then I started going into more detail about how different ways of defining fairness have appeared in the literature over the past 10 years or so. Right? So we talked about these basic ideas of group fairness, different kinds of group fairness, statistical discrepancy, disparate impact, equalizing odds. We also talked about this other idea of what I call individual fairness, which is defined more in terms of differences between individuals and not sort of a group notion. Right? All of these ideas came about in what we would call in machine learning a batch setting. So in a machine learning batch setting, the typical training pipeline goes something like this, right? So you have your training data that gets put into your learning algorithm. Out comes a model, and then you run your test data on the model. And you do this cycle over and over again until you're happy with the model you get. And then once you're happy with the model you get, you have the model, and that gets run on the unseen data. And you make the decisions. And there's this kind of barrier between these two, right? In the sense that in the batch mode world, you have a batch of data, you build your model, and then once you build the model, you kind of throw it over the fence to the people who are going to use it, and they use it, right? But this is only one framework for doing learning. There are other frameworks for doing learning. One of them is called online learning, right? And online learning, what happens is that you don't have this idea of training data, test data, and a model. What happens is an item comes, you make a decision. After you make your decision, you get the answer. Then you update your model, so on. This keeps happening, right? And more generally, there's this whole area of what is called reinforcement learning, where you don't even get the answer to your question. You get some kind of reward, right? So you do something, you get some reward. You do something, you get some reward. And based on that, your goal is to try and maximize the amount of reward you get. In these settings, the way we've defined notions of fairness doesn't quite fit very well. If you have to tally up things like, okay, how many predictions were made for this group versus how many predictions were made, how many decisions were made for the other group, and compare them, this assumes some kind of batch model where you can actually calculate these numbers. But if items are coming one by one, you have this running total that's happening on the fly. You can't actually define these notions in a reasonable way. So then if you are trying to do learning in this sort of online, sequential reinforcement setting, and you want to encode notions of fairness into your process, you have to think a little bit differently. You can absorb some of the same ideas, but you have to express them in your model a little differently. And so there's been some recent work on trying to capture fairness in such contexts. And I should mention these contexts are also interesting because they are in some sense, the first step towards capturing the idea of feedback in your system. So it's one thing to say we build a model to, say, give loans to people. Okay, but let's say you start implementing this model, and some people get loans, some people don't get loans. Because of that, now, sort of you have these bifurcating paths. The people who get loans maybe go and do something else and apply for a loan. Other people who don't get loans because of your algorithm decision maybe come back and apply later on. And now the fact that they haven't got a loan before might be used as a mark against them. We talked about previous history of credit, right? If you get denied credit, that often is a black mark on your application. So let's say you have an algorithm that is saying, okay, if you've been denied credit before, we don't want to give it to you again, right? Because there's some past experience of you not getting credit for whatever reason. But suppose the reason you didn't get credit is because the same algorithm denied you credit last time. Then it's not an independent piece of information, it's a dependent piece of information, and then this process will just perpetuate itself. And so once you get denied once, you will make it harder and harder and harder to get approved again with the same basic information about you in the system. So capturing this idea of what happens with feedback is a hard problem. I will not actually say much about it because we don't know the answer to this, how to deal with this yet. We know that there are problems, we don't know how to fix the problems. But what we can say is, okay, let's think of a setting where you are making decisions on the fly. How do you define fairness in such a context? How do you define the effectiveness of an algorithm in this context? And to do that, we have to go back to a more basic sort of question of how do you define a machine learning algorithm? How do you define a cost function? How do you define quality of a solution in this context? And so that's what I want to talk about a little bit, this idea of sequential learning. Okay? So to do that, sorry. Pardon me? Yeah. So to spell out the point, the idea would be that if you use a time lag where after some time you essentially forgot what you saw before, then maybe this could solve the problem. So in other words, if your model is getting data and it's building some, so your training system is getting data and building a model based on that, and let's say after some time period, it starts all over again, it sort of refreshes. That could be one way to do this. And then of course you have other questions like, okay, what is the appropriate time frame? Can we get a month of data? Can we get a day of data? Can we get a year of data? And then you could imagine that the people using the system might be a little reluctant to throw out all the data because, some of the data might be good, right? And the more data you have, the better the model is going to be. So if you start throwing out things after a month, you have this, month-long Markov chain, and now you don't have any persistent memory beyond a month. And is that a good thing or not? So the question is, do we have to do that? Is there any other way to get around that problem, right? I mean, it's definitely one possible solution to the problem, but I don't think it's the only solution or the best solution to the problem anyway. Okay. So let's talk about sequential learning, right? What does it even mean? Sorry. Okay. So I will limit myself to one very standard setting for sequential learning. I'm not going to, there's a whole array of sort of mechanisms that people have looked at. There's some very nice books on this topic that I encourage you to go look at. I will put some references in the notes for things you can go see. So if you look at basically, things like reinforcement learning, which is all the rage right now because of robotics and because of learning to play games, right? So you play a game, you do something, you get a small reward. You do something, you get a small reward. So reinforcement learning is sort of back in vogue again because people have figured out how to do reinforcement learning with deep learning, and it's sort of an interesting topic. And I'll just put on these names here. I'm not going to go into details in any of these things or even talk much about them. I just want to use it as a vehicle to talk about this particular notion of fairness. Right? And so in this context, again, remember, the game is going to be the following, that you're going to take some actions, you're going to get some rewards, and the game over time is to maximize your reward. Let's be more specific. One of the classic models for thinking about the learning in the setting is what is called the multi-armed bandit. How many of you have heard of a bandit or a multi-armed bandit in the context of learning? No? Okay. All right. So the name comes from a particular kind of slot machine in a casino. And I don't know if you've ever seen this kind of machine. So basically it's a machine, you pull a lever and the dials go, and if you get 3 hearts or 3 apples or whatever, you get a bit of money. Otherwise you don't. You put a coin in, you pull. You put a coin, you pull, and you keep pulling. And you could spend hours doing this. There are places in the US where at the airport, they have these machines there, so you can just like waste your time and your money just pulling it. So it's a gambling device, right? And so you take an action which is pulling a lever, and so you imagine this machine here like this. It's got all these, levers here. Right? And the hope is that you pull a lever, something will happen. Right? So let's assume for now, you have K of these levers. And the way the game is played is the following. So you pull a lever, okay? And below each lever is a little box. And the coins fall into that box, if you're lucky, okay? And so associated with the machine, so the designers of the game, you don't know what they've done, but the designers of the game have set up a reward system that basically says that if you pull the jth lever, okay, your reward that you get is some random variable, okay? It's drawn from some distribution with, let's say it's an unknown mean, mu j. Okay, so there's a distribution and a reward mean value for every bandit, okay? Every arm, which is every bandit. So when you pull, if your action, so you take an action, so your player, you take an action, pull lever j. And the reward is going to be some rj which is drawn uniformly from DJ. Okay? This has to be a distribution, right? Because otherwise what will happen is you can just pull each lever once, figure out what the rewards are, then do what you want. So the multi-arm bandit system is a very easy, simple way to capture this idea of exploration versus exploitation. So think of yourself as exploring an unknown environment. Let's say you're a robot, right? So you're exploring some unknown environment, and you're trying to pick up coins on the ground. One option available to you is to stay where you are and keep picking up coins around you. This is what you would call an exploitation strategy. Exploit the situation that you're in right now. Right? Another strategy where you say, well, I see some coins here, but maybe out in the fog, it's 8 o'clock in the morning, there's fog everywhere, but if I just went through the fog a little bit, there's a whole pile of coins there. I don't know if it's there, but maybe it's there. And if I don't explore, I will never know, right? Maybe I started off in a bad area, but if I could explore a bit, I come to this area with piles of money. So this is explore tension there. And so what this bandit captures is this tension between these strategies, that you somehow would, if you knew all the mues ahead of time, if I told you what the values are, it's easy. Just pick the one that gives you the best value, right? But if you don't know, somehow you have to explore. But in the process of exploration, you might end up getting less reward than you should. Of course, the question is, what does it mean less than you should? What is the cost function here? What are you trying to optimize? I can happily go around, pull levers, get reward. The game is not so much to get some reward, it's to get the best reward possible, right? To define the best strategy possible here. So what that means, you have to compare against something. If you want to say, I am best, you say best compared to what? So how do we define best here? So in most of these settings, the way you define best is with a notion called regret, right? I should point out that, you can remember all the things you've done. So in the first step, you pull lever 1, you got some reward. You're allowed to remember that because that's useful information for next time. Right? So you can keep track of all this stuff. So the idea of regret is this, right? It's a regret for the path not taken, right? So it's sort of a very poetic name for a sort of a cost function. It says, I did this, but I regret doing this because I should have done that, right? So how do you capture that idea formally, the idea of regret? Now, it's not hard to see that, you have to limit what you compare against up to some point. Otherwise, it'll be completely impossible. If you have for example, suppose you had an adversary you're playing against, and this wasn't stochastic ending, and they could decide what reward you get every time you pull the lever. Then every time you pull the lever, they would decide, okay, that's the one where you get no reward, and you'll be dead compared to anyone else. So one way to think about how to measure regret is to say, okay, if I knew everything ahead of time, and I wanted to find the one best answer, okay, the single best answer, how well do I do compared to that? Right? Another way of thinking about this problem is, one way of thinking about this is that, you're taking advice from a bunch of people. You're consulting them. You have a whole collection of advisors, and every life choice you make, you go and ask your advisors, right, what to do. And the advisors are, they have their own agenda. You don't quite know what they're doing, but when you ask them, they give you some answer. You take the action, and something happens as a result of that. So that's a reward you get from pulling the lever by asking their advice. Now, you don't know who's doing what. You don't know what they're telling you. What you'd like to know is, okay, if there was one smartest advisor there, you would do at least as well as they do, or at least close to what the smartest advisor would be telling you. So that if you fired everyone else and asked that one person all the time, the rewards you'd get would be comparable to what you're getting right now. The catch, of course, is you don't know who the smartest advisor in the room is. You only have this pool, right? You don't know who to fire. So somehow you have to play some game where you ask the advisors questions, you try out what they have to say, but overall, in the long run, what you get is an answer that is close to what would have happened if you fired all the advisors and chose one to give you all the answers. So the way to formalize that idea here is to say, compare yourself to the best possible single choice. Okay? And see how well you do. Okay, so let's think about this. Suppose I moved the curtain away, I opened up the machine, and you could see all these things, the numbers. You knew what the mu-j and the dj were for each lever. And then I asked you, what is the maximum expected reward you can get? Now, this is an expectation because These are distributions. You're not getting a same reward each time. You're getting a reward which is from a probability distribution, right? So what is the maximum expected reward you could get if I told you everything in one time step? Sorry?
The one with highest mean.
So what you're saying is look at all the levers, choose the one that has the highest mean, and pick that one. And that's in fact what you would do. Why? Because you're looking for the best expected reward. I'm not worried about variations and sort of and how far you deviate. In expectation, because expectation is linear, the best thing to do is to pick the one that has the best expectation itself. So let's say there's some J star, which is equal to, arg max mu J. Okay? If you knew ahead of time what you should be doing, then this is the one you should pick. Right? Okay. So let's think of this process going on for T time steps, capital T. Okay? And let's say if you knew ahead of time what you should do, you would pick this one each time. So how much reward would you get? The expected reward you would get would be, right? Because in every step, my expected reward is mu J star, right? Linearity expectation. Okay. So this is what you should get. What you actually will get will be something else. It probably won't be this, right? And the difference between the two will be the regret. Okay. So what is it that you're going to get? Now let's say you have a sequence of actions, right? So you take a sequence of actions, and every step you pull, so let's say your actions are denoted as I1, I2, up to IT. IK is the lever, the index of the lever you pull at time K, okay? So what is the value you're going to get with respect to this? So the value you're going to get is going to be the expected value, right? Okay, so let me back up a second. Sorry, let me back up 1 second. Yeah, if I picked a single lever each time, I would know exactly what I was getting. There'd be no expectation. But let me change the game a little bit to make it a little bit better for you. What you're going to do is not, your action is going to be to pull a lever, but the way you're going to choose which action to pull is going to be via a policy. So the policy, let's say, so the policy at pi t, at time t, is a distribution over the set of all levers. In other words, what I'm going to do as an algorithm is not decide every step, pick this, pick this, pick that. In a more sort of, if you want to say Bayesian sense, I'm going to maintain a distribution of hypotheses over my experts, over my levers. And then I'm going to pick a sample from the distribution. In other words, I'm going to say, okay, in the beginning, I believe all my advisors are great. So I'll just pick any of them to answer my question. Then I'll get an answer. It's like, oh man, this advisor lost me 100 rupees. Okay, fine. I will downweight that advisor's importance a little bit. Now my distribution has got a little dimple in it, right? Dimple in it. And now I sample again. So I'm a little bit less likely to sample that advisor, maybe. I'm not saying that's exactly what will happen, but that could be what happens. And so as time goes on, I will have some kind of distribution over what I believe to be the right set of advisors. And of course, the distribution could be a single point, which is the case when you always know which one to pick. Or it could be something more general. So, but think of the output of this process as a distribution over advisors at every time step. Okay, so the first point comes, the first time you say, okay, pull a lever, you pull a lever, you get some reward, you update your distribution over the advisors. Next time step, you sample from this distribution, pick an advisor, pull the lever, get the reward, again, update the distribution, and so on. So in that case, your expected reward is an expectation over this sampling here, right? So in other words, if I now choose as a result of this policy, I now choose again actions I1 to IT, right? Then my reward is going to be the expected value of sum of mu I k, where this expectation is taken over my policy. In other words, it's taken over the choice that I make at every step. That make sense? So again, what I'm saying is that this is the ideal reward I would have got if I knew everything. This is the reward my algorithm is actually going to achieve. And this difference is called regret. And obviously I want to minimize regret. Maximize reward, minimize regret. Right? The smaller I can make this, the happier I'll be. Okay, any questions so far? Pardon me? Sorry? Okay, the policy is in some sense you can think of as the state of the algorithm, right? So think of me as the algorithm. I'm deciding which lever to pick. The way I'm going to pick a lever is pull lever J, sampled from pi t. Okay? And then, so that's step 1, step 2, and then step 3 is update pi t to pi t plus 1. So again, just to emphasize the difference in the batch setting, it's not like I'm getting any right answer, wrong answer. I'm just getting some reward, some profit, some kind. And what I'm doing here is trying to say, okay, look, think of what's happening here. In the beginning, for example, I might start with a uniform policy over all levers. You can think of this as a full exploration mode. I'm willing to try anything. I pick a sample, I get some reward. I update my distribution in some way, and there are some clever ways to do this that I won't get into. But there are ways to update these distributions. You can imagine, again, this sort of little bit of upweighting, downweighting of your things. And then I might explore again. Over time, my explorations will hopefully have created a kind of peaks in my distribution. Advisors that are reliable and are giving me good rewards and advisors that are not. And so I'll start exploiting a bit more by sampling from this more skewed distribution. And eventually, if all goes well, I will be narrowed in on one particular good distribution here. Again, you can think of this as a function of time. And so often we look at regret and say, okay, as a function of time, how does this behave? Right? So unlike a batch setting where you say, okay, I have a fixed data set, I look at the amount of errors I make, you can think of this as an ongoing process. So this is a limiting process. You don't think of this as a one-time thing. You say, as a function of time, what happens to this? For example, if you look at the average regret, right? So you look at this divided by t, you'd like that to be a constant in an ideal case, right? That over time it doesn't change or it goes to 0 even, right? I mean, ideally, in fact, so the best algorithms for online learning, they will actually end up setting this to 0. But this is the setup here, and this is one of many standard sequential learning setups. Right, when you have actions and rewards. So this is more general than online learning, which just talks about online feedbacks. An online learning setting would be, I classify the item, and then I get the true classification back, I update my score, and I do this again. This is more of a question of actions and rewards. We don't really have a yes or no answer to questions. And so you can think of now, in the context that we have been looking at, in the context of decision making, that you can think of the choice of a bandit, if you want, as say choosing a person. So you select a person for hiring, and now because you have some distribution over people, based on this you select some quality distribution over people. It's okay, I'll select this person, and you get some reward based on how good the decision was, and now you want to update this process. And so the question is, what does it mean to be fair in such a context? None of our definitions of fairness will work anymore. Okay. So before I give you that definition of fairness, do you have any questions about? You don't know the actual regret ever. No. But you can prove bounds on it. Right? It's like if you've ever taken a class in algorithms, right? These things called approximation algorithms. You have some problem that's NP hard. You want to solve it, you can't, but you can get close to it. You can't solve the problem, so you don't know what the optimal solution is, but you can prove that you get close to the answer. And so in the same spirit, even though you may not be able to show exactly what the regret bound is, what the max reward is, you can prove that you always get close to it. And intuitively, some of the, I mean, again, I don't want to go into details of the algorithms used to solve these problems, but let me give you if you think about it for a second, what would you want to do? So we already have one clue. We know that if you knew all the mu's, you would do the right thing. Because once you know all the mu's, you can just choose one lever and pull it. So what do you think a strategy might be here? Sorry? So in other words, so why would you use chi-square? Why do you want to differentiate among the distributions? Right. So if you think of this, if you think of trying, the goal here, the goal is to try and estimate these means somehow. So one obvious strategy is, okay, take the first lever, pull, 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 pull. You pull enough times, you will get some estimate of the mean. Then take the next lever, pull, pull, pull. Pull enough times, you'll get some estimate of the mean. And do this for all of them. Clearly, once you've done this for all the levers, you will have pretty good estimates of all the means, and then you can pick the best one. But in the meantime, while you're pulling all those levers, you've probably incurred reward that's, every time step, think of it, that every time step is ticking away. The optimal solution got mu j star, and you got something because you were fooling around with some lever. So maybe this algorithm is not optimal, right? It's very suboptimal because you're wasting a lot of time. So if you think about it, what is the goal here? The goal is to find the maximum of a bunch of entities, right? All you can do is get a value for what that entity might be, an approximate value by sampling from it, but you want to find the max. Now to find the max, suppose if you think of these levers, okay, let's draw here. This is good to sort of think about, right? Suppose you have these three levers. I'm going to draw them on the line in terms of the rewards. This was lever 1, lever 2, and lever 3. Their means are here, and one lever's distribution looks like this. One lever's distribution looks like this, and one lever's distribution looks like this, okay? Now, you're probably very quickly going to figure out that this is not even in contention. There's no way this is going to be of use to you. And if it's concentrated enough, you will hopefully figure this out very quickly. Like you take a couple of samples from here, a couple of samples from here, you will realize they're so far apart, there's really no point looking at this one, right? Whereas here and here, you're not quite sure. You got to do a bit more work to figure out, okay, this is actually better than that because they overlap. So in some sense, what you're trying to do with your algorithm is figure out very quickly whether I can say with some confidence that two levers have rewards that are significantly different from each other in the mean sense. So I can discard one. And so the best algorithms for this problem do essentially that. With some more details and more specifics about how you go about this. But they basically maintain confidence bounds around the expected values of all these rewards to say, okay, I can now rule out certain levers, because they're too small for me. Okay? So that's the basic idea of how the algorithms for this kind of problem work. So you explore for a while, and then you exploit. And how you do it depends on the situation. Okay. So now, like I said, if you think of this as a decision-making process, these levers, let's say, are people. Right? You're making a decision about a person, you're pulling them, maybe the pull means send them off to the company that you're hiring them for. And you want to have a notion of fairness. And so this is how the notion of fairness is then defined, or at least has been proposed in this setting. Again, this is all new stuff, right? So when I say it's been defined, this is one proposal. There may be others as well. So this is how it looks. The intuition behind the definition of fairness here, and maybe it'd be good to sort of see if we can recreate the definition ourselves rather than having me just tell you. If this was a decision-making system, and if each lever was an individual, what might you think would be a plausible way to define fairness in such a system, based on all the things we've talked about before? Yes. That's up to you to define. I said, you define how you want. Fairness in the decision-making process in some way that you choose to define. Okay, that's the idea, but how would that translate into the setting? So how do you translate the idea of every individual should get a chance to participate in this setting? You have to pull every lever? Every lever it should be possible to pull every lever maybe? Is that what you're saying? Like your strategy should not ignore any levers? Set of all? All means, okay. Okay. But if you want to maximize reward or minimize regret, if you look at the definitions of fairness we've seen so far, right, have any of them said everyone should get an equal chance? They haven't, right? They've said things like, there should be no reason to discriminate against one group, or everyone should get a chance. People who have similar skills should get similar potential for, hiring or whatever. But we haven't said everyone should get a chance, because, there are natural, merit-based requirements that might say you don't want to pick certain people. So keeping that in mind, right, what might you do here? Pardon me? The reward distributions or the pie? But that's the world, that's set from someone else. You don't have any control over that. That's the environment.
So there are two groups, one productive group and one not. So if UJ appears in one group or appears in a group, so the regret should remain the same.
The what?
So
the regret.
Yeah.
Okay, but the regret is a function of your choices.
Yes.
So if you think of fairness, fairness is a constraint on what your algorithm might do, right? Here, what is the algorithm? What are the only things the algorithm does? What does it produce?
Pi.
It produces pi. So any definition of fairness you're going to define should somehow involve pi. Now tell me what you think.
Pi is independent of the group we don't want to discriminate upon.
Let's keep it even simpler for now. Let's forget groups. Let's think of individual fairness. I just have individual things. But you're kind of on the right track. So I have just individuals. I want to make sure I have some notion of being individually fair. If you remember from yesterday, we talked about notion of individually fair. How would I define that here?
Similarly, superior people should be treated similarly.
Well, anyone else? Okay, this is a test, right? See, I'm asking you to apply something you learned yesterday. This is part of your quiz. I'm taking score here. So again, we've agreed that, we've said that fairness has something to do with how you pull the levers. We've said that fairness should be encoded in some constraints on the product of the algorithm, the pi. And so what might that be? So remember that the choice the algorithm makes is to choose one lever and not choose another lever. That's where the decision is being made, right? I'm choosing J, I'm not choosing J prime. So it's at that point of choice that we want to say, hey, are you doing the right thing? Are you doing the fair thing here? So you're saying look at the two levers, look at the expected mu. Of course, you don't have the expected mu, but you can say based on that you want to do something. Okay, this is good. This is getting very close. This is good. We're almost there. So let's say we knew what the expected. Okay, let's think of it this way. So taking your idea there. So we have the levers J and J prime, and let's say someone whispered into my ear. So there's the algorithm running. I'm the auditor. I'm saying, okay, are you being fair? And someone has told me what mu j is and what mu j prime is. And now I'm watching the algorithm perform. What would I want to see from the algorithm, knowing these? Or what might I want to see? Again, all I'm seeing from the algorithm are the pi's, right? So what might I want to see from the algorithm if someone has told me what mu j and mu j prime are? Going back to your idea. So what would be a discriminatory action in this case? So we're looking again this pairwise thing. We're looking at just two levers. You either have the choice to pick this one or this one, right? The discriminatory action here would be essentially picking one versus the other in some inappropriate way. What would be an inappropriate choice of picking here? If I've told you what mu j and mu j prime here, what would you expect to be the reasonable thing to do?
If we are considering every individual as a vector form,
As a lever, yeah?
their ortho will be bigger. So
Sure.
we'll consider that individuals who have maximum variance among it. Like the variance depends on mean value.
We don't actually know what the variances are, and they don't depend on the mean value, right? The variance of a distribution has nothing to do with its mean. So all we have here is the mean. But here's what we could do. We could say, look, if I've been told that this, is more than that, that's it. Okay? So it would be reasonable if I saw, in some aggregate sense, because it's a randomized process, that the algorithm was preferring this to that. If I did not see this, if I didn't see this relationship, if they were, equal, or it was the inequality was the other way around, so let's say I saw it the other way around, and yet the algorithm was preferring this to that, I might say this is kind of strange. Why is the algorithm preferring one to the other if I know, because I've been told that this is strictly different? That doesn't sound individually fair. Sorry? So the proposal for the definition of fairness says this. Let's look at the policy described by the algorithm. So the algorithm produces a policy, this pi, right? It says, okay, this is my current distribution over the preferences for the individuals. Okay? And let us define okay, so let me back up a second. Let me introduce some more notation here so I can explain what's going on. So let us now say that the history at time t, say ht, is the history of all the decisions the algorithm has made so far. So the algorithm is a complete record of everything it's done so far. Okay? Now, based on that, right, we can say, okay, what is the algorithm going to do at time t? And in particular, we can define pi t j given h as the probability that the algorithm picks j taken over all histories. So one way to think about this is, what does this mean? It means you imagine running the algorithm a gazillion times with the same inputs and the same, sampling of rewards. And at time t, stop it and say, okay, at this time t, I can look at my policy and say, what is the probability that I'm going to pick j? Because I have a distribution over all the arms. I write that down. And I compute this. I compute this probability over all possible histories. Okay? This, in some sense, captures at this point, at this time, what is my chance of picking j? Right? And I can do the same thing for j prime. Right? I can have the same number for j prime. The reason I want to compute these quantities is because this number expresses my algorithm's bias, if you wish, for picking j. And pi j prime th is my bias towards picking j prime. And so what the definition of fairness says is that an algorithm A is delta fair. I'll explain what delta means in a second. If for all possible distributions over the arms, so all possible real world scenarios, okay, which means all possible mu's, okay, and with probability 1 minus delta. So think of delta as a very small number. So 1 minus delta is a very large number. So with high probability over the history, for all time and for all j and j primes. Okay, so for all pairs of arms over at all time steps, then what we want is that the tendency of the algorithm to pick j is okay to be more than the tendency of the algorithm to pick j prime, okay, only if it was justified. So this goes back to the point that you were mentioning earlier. You're saying, okay, look at the mu j's, and if one is bigger than the other, then it's okay to sort of discard one. What this is saying is that if one is bigger than the other, it's okay to prefer one. So we're not discarding, but we're preferring it. It's the same idea there, right? Delta is a tuning, sort of think of it like a tuning parameter. It's a randomized algorithm, so an algorithm has some probability of success, so you want to make, think of, if you don't like delta, think of delta as 0.01 or something, some very small number, right? Basically what you're saying, almost certainly is the catchphrase for this. So what this is saying is, in all worlds, almost certainly, for any pair of people at any time, your algorithm does not prefer one over the other unless there's a reason for it. Okay? If you think of the contrapositive of this, what it's saying is that if there is a true, if there's a true difference, it's okay to treat them differently, which is very much like the individual fairness decision we saw yesterday. And so you can think of this as a kind of sequential version of an individual fairness decision. The reason you have to set it up this way is because the algorithm is no longer making single decisions, it's making this kind of distribution of decisions. It's giving preferences in a student's way.
Preferences for someone is being unfair.
Exactly. Yeah, exactly. That's the way to say it. Right.
So it's very similar to optimality, right?
It is. This has been a question I have been pondering myself as to why this is not just optimality. But it's another way of thinking about is unaccounted preferences, right? So the only justifiable bias is coming from the real world. If you have some bias that's not coming from the real world, I'm not saying you're unfair, but that there's no justification for it. It's unaccounted for. Yeah, I actually like that phrase of yours. I'm going to write that down here.
You mean to say there are two teams playing football now?
Sorry?
There are two teams that are playing, say, some game, say football, and in the final, somebody who's tipped to win doesn't win because of no apparent reason. And you say that there's some problem.
And that's often how we look at evidence of betting in tennis matches and things like that. Sorry?
You start eyeing people with.
Right, and suspicion, that's all. We're not saying there's a problem, but there's something weird going on. And that's where this tolerance parameter allows you to weaken or strengthen the amount of suspicion you have, right? If you make this very large, then you say, okay, look, some of the time it should be there, but some of the time it should not. If you make this very, very small, you're saying, look, almost all the time, your answer should be consistent with what the world is telling you. So this is again your tuning. So we talked about tuning parameters for fairness. You can think of this as your tuning parameter for fairness in this case. The degree to which you expect consistency or accountability for the preferences with respect to the underlying domain. So this is a far more complex notion of fairness, a more subtle notion, I think, than many of the ones we've seen, necessitated by the more subtle setup for learning that we're dealing with. Right? And if you think of scenarios like predictive policing, where if you think of, you send police out, they either observe crime or do not, they come back, you can think of this as happening in some kind of sequential process. So there's a reason to think about this framework and the reason to think about fairness in this framework. There's been other work on this to extend this to ideas of group fairness and all, but I want to introduce this idea itself as a continuation of yesterday's discussion so we can just think about, okay, how does this whole process work? Okay? All right. Any questions?
Did you capture the version where
the distribution still changes because of the actions. For example, in predictive policing, like because police patrols black areas more, so black is caught more because families get broken and there are more crime.
This is a complicated issue. This is one of the things that I'm actually working on right now, is trying to understand exactly how to model the idea of distributions changing as an effect of your input.
So all of these are,
I'll have to edit that from the video because this is all secret right now.
all
That's
these
fine.
are black box approach to design. All the definitions. Look at the input, look at the output, and define. So you're not
Yes, that is correct. That is correct. And you could try to instrument, yes, in all of the definitions I've given so far, these are black box processes. You're not looking at the process, and I think this is partly by design, because you don't want to have to think about the process. Your judgment, your belief is that I should be able to declare fairness or bias just by looking at the inputs and outputs. I shouldn't have to, the process should not matter.
No, but we can look at the intermediate stage.
You could. So you could, of course, the black box could be made into a bunch of smaller black boxes, right? That's also true. But I think the idea of a black box at some level is interesting also because for two reasons. I think in the law, if I felt bad about killing someone, it doesn't mean I'm any less guilty of doing so. That might be used in some ways to mitigate the sentence I get, but I'm still guilty of killing someone. So intent is often a part of the process of deciding whether someone is responsible for a crime, but mental state doesn't only, well, it sort of partly figures it, but in a complicated ways.
But the conditions for that crime, why was the crime at all committed is important when there is culpable homicide, non-culpable homicide.
Right, so the circumstances of the crime are important, but the fact that the crime was committed, it is not, the fact the crime was committed is not, well, I should be careful here because there are mitigations based on your mental state and a crime of passion or something like that. Yeah, so that stuff is not captured here because this is purely, okay, I don't care what happened in the middle, but I see the input, I see the output, there's a problem here. And I think, now that I think about this, it might be interesting to ask, okay, if you had to bring in more nuance into the definition of fairness to allow for mitigating circumstances in the procedure in some way, how would you do that? And I don't think anyone's ever done that. Anyone's ever tried to think through what it means. The problem is that algorithms can be obfuscated. A black box can be hidden. Even if I say I know what the algorithm is doing, there are ways to redo the algorithm and make it impossible to tell what it's doing. So you can sort of essentially cryptographically encode what the algorithm is doing, so you have no way to tell what's happening inside it. So if you did have a process that depended on knowing what the algorithm was doing, it could be broken easily by obfuscating. But nevertheless, I think it's still interesting and definitely are. So again, when I say interesting, I mean there's a research direction to explore here. How to think about these fairness ideas when you actually want to define them as functions of what the procedure is doing as well. That's a good sort of thing. In fact, that's a good point to sort of stop and sort of take a minute to think about this, because I'm gonna now stop talking about definitions of fairness and start talking about actual doing something with it. But before I do that, are there any other questions?
Just one last one.
Yeah.
Any system can be characterized if you have exhaustive list of inputs. So can you talk about that? What can be the possible the complete characterization?
Well, first of all, if you have distributions, then describing the distribution can take many, many bits. Because I can have, potentially, very small numbers to decide. I might have, for example, I could have one arm be, let's say, sorry. I could have a distribution of rewards, let's say a Gaussian. Right, so I have all possible rewards from -infinity to +infinity with tiny probabilities. Now, when you say I can list out all possible eventualities, how am I going to list that out?
Really, but what I'm saying is the definition of regret, for example, you just mean
Yes?
so if you use more moments,
Yeah.
then probably you have a better picture.
So I'm not as familiar with the online learning literature. I don't know if people have tried to define regret in terms of higher moments or just expected things and stuff like that. I don't know. There are worst case versions of these things as adversarial regret and all, but there may be, yeah. Okay. So this, in some sense, is where I ideally would have ended yesterday's lecture, at least sort of content-wise. The whole story arc for this, what I talked about yesterday was how you define fairness in different contexts. And so this is the last piece of the puzzle, not in terms of these capture all notion of fairness you can think of, but these capture the notions we've seen so far in the literature. And as we are discussing, there could be many others as well. Okay, so at this point, so I'm going to sort of stop here and then change gears to the next topic.